And then we're going to briefly talk about two topics. Right now, I assume some of you are taking the class of 5106. Essentially, that class is focusing on, read to yourself, thermodynamics. Thermodynamics, which is related to equilibrium, related to energy difference. Quite often, you are talking about standard free energy change, Gibbs free energy change, and equilibrium constant. Maybe you saw this reaction, delta G reaction. Delta G. Delta means what? The change in free energy for Gibbs free energy for the reaction is the standard change plus a reaction condition term, RT log K. Okay? All the other way, constant, equilibrium constant K, we can get it exponential of that guy. Make sense? That's what you are learning in thermodynamics, the free energy change and equilibrium constant. And quite often you are talking about direction of reaction or possibility of reaction. If the free energy change for a process is negative, means what? The process would be so-called spontaneous. I burn oil, I burn gasoline. That's spontaneous. I have a hydrogen. In air, I light up a lighter, it's going to combust or explode because it's a spontaneous process. It happens quickly, naturally by itself. Okay. On the other hand, if the delta G is positive, means what? It doesn't really happen unless you help it a lot. You are putting a lot of energy into it. For example, when does aluminum oxide naturally produce metal aluminum? Does aluminum oxide naturally produce the shiny white natural aluminum? No, you have to spend a lot of what? Energy, electricity into the system to get aluminum. From aluminum oxide to aluminum, that delta G under normal condition is highly positive, which means it doesn't happen no matter what you do. But to overcome it, I have to supply what? A lot of electricity, then I can make it happen. That's what you learn in thermodynamics. How much energy you have to put in. Okay, and the next semester, the class will be about kinetics, which some of us have already taken. Kinetics, it's quite often about what? Read to yourself, extent of reaction. I'm doing this combustion. It's my reaction 1% complete or 100% complete. Extent of reaction, okay? Or rate of reaction. What does that mean? It's how fast does my reaction happen, right? You find your typical carbon steel, you put that in seawater, it rusts what? Quickly, right? You put a typical carbon steel in seawater in Miami, quickly become rusty within day, literally in front of you. On the other hand, if you put a stainless steel into the ocean water, you find a high quality 304 or 316 stainless steel, it probably doesn't rust. You put a piece of aluminum in there in seawater, also doesn't really rust. Aluminum probably not as good, but you put a piece of titanium, I assure you, in seawater it doesn't rust. Which means the rate of reaction is what? Very slow. Okay, that's what will be concerned in kinetics class. Kinetic curve. The extent of reaction versus time. We have different types of kinetic curve. Some of them start with slow, gradually what? Getting faster. The vertical axis is how the extent of reaction. The horizontal is what? T for time. Okay, some of them gradually become faster, self-accelerating. Some of them accelerate and then what? Slow down. Make sense? Some of them goes initially very, very fast, but eventually you have to slow down. Why? Quite often corrosion product that inhibits, or you used up, right? You have nothing to consume. Your reactant concentration become lower. Let's say you carry out a precipitation reaction. Towards the end of your precipitation reaction, does that stuff coming out continuously? No, because you have a limited supply of reactant, and at a certain point you have nothing to react, and of course it slows down. Make sense? So that's what kinetics about. Kinetic models, different model we will talk about in next semester. To mathematically describe the relationship between external reaction and reaction time. Reaction mechanism. How does the reaction happen? Okay. What are the so-called rate limiting steps? Is that diffusion or some other step? And the impact of processing factor, temperature, size, scale of mixing. All these things are different. Microstructure evolution. With that, microstructure is very, very important. Quite often, between the loosely bonded sand versus a high purity quartz container, what's the difference? You get a scoop of sand from the ocean just by the beach. Well, by chemically, it's pretty pure silicon dioxide. And then your lab, we have the so-called clear quartz tube. What's the difference between those two? Not in chemistry, they're pretty much same, but in structure. That quartz is pore free, right? Everything bonded together. That sand is individual particles, right? That's porosity in there. You can use quartz fused to do your gas processing. You can do that for container. You use loose sand. That only come as a raw material. Make sense? So microstructure very, very different.